So in this video, we're going to practice adding vectors in a more complex way. We're going to start with two vectors that are, I want to make one blue, I'm going to make the other one brown. All right, and you'll notice that they're both pointed down and horizontally, right or left, and relative to a horizontal. Usually I like to do a dotted line for my horizontal. And this is just showing us, it's giving us a point of reference for these vectors. And so this brown vector is pointed 8 degrees down from the horizontal, and this blue vector is pointed 40 degrees down from the horizontal, but it's pointed down and left, whereas the brown vector is down and right. So over here on the on this coordinate axis I have here, I'm going to go ahead and label, oops, see if I can straighten that out a little bit. I'm going to go ahead and label what positive, or what up is, right, left, and down in terms of positive y, negative y, and then positive x and negative x. Once again, I could call, positive x left or positive y down. I think this is just the way that makes the most sense. Now, both of these vectors are at some angle. Let's see. Relative to the horizontal. This one 40 degrees. This one 18. And they both have different magnitudes. The brown vector has a magnitude of 10 meters per second, so slightly shorter vector. And the blue vector, 12 meters per second, so slightly longer vector. All right, so what we're going to do first is do the same thing we did last time we added and subtracted vectors, which was to just add the vectors head to tail and draw a resultant. And this is a fairly good way of adding vectors, but it's an approximation, is kind of the idea. What we're going to do with this assignment is make our vector addition a lot more accurate. So this is going to be better than the approximation. But just for just to kind of have an idea of what we're doing here, just a general idea, let's make the approximation, right? So what I'm saying is, let's see what that approximation would look like. What exactly are we going to get here? And if you want to draw the relative, I was going to say, if you want to draw the black dotted lines down here, you can too, but I'm just going to go ahead and bring them down and just brown and blue and put them about approximately what they're doing up there. So I'm saying it's going to kind of look like this, right? Because if I drew in the black dotted lines, this would be my 40-degree angle. And I'm not sure how, 45 obviously is in between 0 and 90, but I'm not sure how accurate that is, right? So I'm adding that to the brown vector, which is at that angle of 18. Okay, so once again, I don't need the black dotted lines and the angles down there, but I'm just showing you kind of what it looks like. All right, so now I'm going to go ahead and draw the resultant. So remember last time we said this is like a, whoops, I didn't point my brown vector, did I? Sorry about that. We said this is like a treasure map. So you're going to start right here. You're going to follow the blue vector to the end of the brown vector, then follow the brown vector down and right, and you're going to end about, I got to be careful here because I don't want this brown vector getting a lot longer. It almost looks like it's the same size as the blue vector, when I know it's definitely a little shorter, whoops, I'm going to redraw that brown vector. Just because it's definitely a little shorter than the blue vector. Oops, let's go about right there. So what I'm trying to show you here is I think the end is about right there. And that this resultant, right? Let's go ahead and put it in red. Is going to point something like this. Now the resultant is a vector, right? Because remember we label it with that little vector hat. The resultant is a vector and points from start to end. And that's an important thing that I think a lot of students sometimes forget. I think last time we were dotted lining the resultant, so I can draw that one more time and show you with a dotted line if you like. But let me do it one more time. So I'm saying it's going to point from start to end. Oh, I'm struggling with that. I don't really like that. Still learning how this software works. Really struggling to draw a dotted line. All right, so it looks like it's a vector that is larger downward, but and slightly left. So we're gonna find out if that holds true. This is just a guess. Once again, I'm gonna go ahead and write that down right here. This is just a guess. So that's why we, maybe a guess is a bad word, maybe estimate. We're gonna try to now solve the problem in a way that's much more exact. So down here, what our general plan is before we start getting into the math and the nitty gritty, because it's gonna get kind of just kind of tough with the math. What we're gonna do is we can't add x and y vectors easily. So what we're gonna do is we're gonna resolve both of these vectors into x parts and y parts. We can add the x parts independently from the y parts. Once we do that, we'll sum up the two x parts, sum up the two y parts. If we look up here at our vectors, we can see that brown and blue are going to fight, right? Blue wants to point left and brown wants to point right. And in the horizontal direction of the x direction, those are going to conflict. But in the vertical direction, both vectors, blue and brown, want to point down. So we expect that when we add the y vector components together, we're going to get a larger y vector. When we add the x vector components together, we're going to get a smaller x component. And we'll apply signs, positive for right, negative for left, positive for up, negative for down. We'll then use those vector summations, right? We'll use those vector sums to create a right triangle, and the hypotenuse will be our final answer. Then we'll use inverse tan, and with that we'll be able to correctly describe the angle that is going on there. And so this is better than what we did before, because before we could just say, well, the answer is approximately that red vector, but now we're going to say exactly what that red vector is, and we're going to say the exact angle that vector is pointing. All right, I'm not sure why that's okay. All right, so let's go ahead and break these vectors up into components, right? Components are parts. I'll go ahead and use, I'm going to go ahead and use, I guess just black right now, and we'll see how this goes. So draw and label Vx and Vy. Okay, so let's start with just one vector at a time, right? Let's start with this vector right here. So here it's pointed down and left. And this is, I think this was the blue vector. So when the blue vector points down and left, we're going to go ahead and make it, the parts of it, right, be down and left. So I'll start with the left vector. So I'm starting near its base. I'm going to then point right there. And then I'll start with the down vector. Now, could I have drawn the vectors like this with the down vector first and then the left vector? Yes, this would work too. However, the angle would now be different. This would be 50 degrees. So I want to use the angle I'm given, and I like my angle to be inside my vector components. And that's kind of a important thing there, to just the way you want to set these up, because that's confusing usually. So once again, I'll say it again. I want my angle inside my vector components, so I'm not going to use these components or this 50-degree angle. I want to use the angle they gave me, unless I was trying to avoid it, which that'd be a different story. All right, so there's a 90-degree angle right there. It's always between the x and the y components. I'm going to call this vector vx and this vector vy. All right, even though this vx points left, I'll apply that sign here in a second. Let's go ahead and solve for this. So we have a right triangle. Across from 90 is our hip. Across from 40 is our opposite. Next to 40 is our adjacent. Notice I start by labeling the triangle. Then I see that I want to solve for the adjacent, or Vx. So I'm going to use cosine. The reason I know that is because cosine theta is equal to adjacent over the hypotenuse. And I know the hypotenuse, I know theta, I want to know the adjacent. So I'm going to go ahead and rewrite that. So I have the cosine of 40 degrees is equal to the adjacent Vx over the hypotenuse, which is V, by the way. So just so we're clear, this is equal to V. But I'm going to write it as the number I know, which is 12 meters per second. I'll then multiply both sides by 12 meters per second. Cancel the 12s, cancel the meters per second. And what I'm proving here is that the adjacent is equal to the hip cos the angle. So I'll write it out here. I'm saying that Vx is equal to 12 meters per second cosine 40. But you could have also just said, like I just said a second ago, the adjacent is equal to the hip cos the angle. All right, so let's go ahead and solve that. If we plug that into our calculator, we should be getting a Vx value of 9.19 meters per second. Now, this is pointed to the left, right? So I'm going to go ahead and put a negative sign in here because it's pointed to the left. And that way, hopefully, I don't forget when I sum my vectors together that is a negative vector. All right, solve for Vy. Kind of running a little low on room already. That's okay. So I'm going to do the other formula, y, because Vy is an opposite. So I'm thinking as the other formula, I mean sine. So I'm going to go ahead and I always like to write it out once again so I memorize these. And this is my SOH, right? The other one was my CAH. And I can go ahead and plug in the values now. We can say that the sine of 40 is equal to Vy over 12 meters per second. And once again, multiply both sides by 12 meters per second. Cancel 12 meters per second, cancel 12 meters per second. Got to multiply the other side by 12 meters per second. And remember, the meters per second cancel, the 12s cancel. All right, so we're left with the fact that Vy then is equal to 12 meters per second times the sine of 40 degrees. All right, then from this, we can plug this in our calculator, and we're going to get Vy is equal to 7.71 meters per second. And this is also negative because this vertical vector points downwards, right? And we called, if you remember back up at the top, we called down negative, just like we called left negative. All right, so those are my 2 parts of the blue vector. Let's go ahead and do the same thing for the brown vector. All right. So for the brown vector, let's go ahead and label it brown. We see we got the smaller angle here we're working with of 18 degrees. All right, so do the same thing as before. Solve for Vx first. I like to write out my formula, which is where's Vx? I actually like to draw my components. Usually when I give a quiz over this, I would always have the students draw out the components too. And that way they're practicing this. Label the 90-degree right angle, then start to label the right triangle, because this is my velocity, 10, right? This is my Vx, this is my Vy, and obviously 18 is theta. Go ahead and label op, hip, and adjacent. I'm going to use a different color for this. Maybe I'll use orange. The hip is going to be the 10 across from 90, of course. And here's 90 right here in orange. Across from theta is my opposite, and which is Vy. And next to theta is my adjacent. All right, so we're going to solve for Vx, which is an adjacent. So we're using the ka part of SOHCAHTOA, which is cosine of theta equals the adjacent over the hip. Let's go ahead and plug in what we know. We know that the angle is 18 degrees. We know the adjacent is Vx, and we know the hypotenuse is 10 meters per second. We'll multiply both sides here by 10 meters per second. Once again, cancel the meters per second, cancel the tens, and we'll multiply the other side by 10 meters per second. So you do that to one side, you got to do it to the other. Let's go ahead and solve this then. We're saying that Vx equals 10 meters per second times the cosine of 18 degrees, which is equal to 9.51. Obviously using a calculator for this, 9.51 meters per second. All right, and it does point right, so we're expecting a positive sign. And I'm going to go ahead and write that in red. Even though it's positive and I don't have to write it, I just want to point out what is going on here. And just like the other side had 2 negative components, this component right here is going to be positive for pointing to the right. Okay, so now we'll solve for Vy. Once again, just for space, I'm going to go ahead and write it up here maybe. So we're saying sine theta is equal to the op over the hip. We'll go ahead and plug in what we know. We know that sine of 18 degrees is equal to the opposite, which is Vy, over the hypotenuse, which is 10 meters per second. We'll multiply both sides by 10 meters per second. Cancel the meters per second, cancel the tens, and we're left with Vy is equal to 10 meters per second times the sine of 18 degrees. That's kind of hard to read. Let me rewrite that real quick. All right, so we plug that in our calculator, and we end up getting 3.09 meters per second. I don't know if you, well, let me finish writing this. And once again, this points downwards, so it's going to get a negative sign. That is in red right there. So we got something like that. Okay. So, yeah, that's about it. Plug in my numbers and solve, and that's not really a problem. So we're good here. Now in the next part, what you have to realize is we can't accurately add these vectors when they point in different directions, right? Like I wish I could just say, well, 10 plus 12 is 22 and be done, but we can't. So what we have to do now is add the x parts, add the y parts, and then figure out which vector is represented by those x and y sums. And that's what we're going to do. So down here, we'll sum the x components of these two vectors, right? So what I'm saying is we're going to add the negative 9.19 and the positive 9.51 and get an answer here. So we'll have sum of the variables. This is a Greek letter sigma. It is the capital sigma, right? So this is capital sigma. And then lowercase sigma, I believe, is that. Oops, got a little crazy with that tail there. Let me try that again. I think something like that. And so this Greek alphabet has capital letters and lowercase letters. And yeah, what does this stand for? I think it might mean like standard deviation in stats class. I've actually never taken a stats class, but I'm pretty sure it's something like that. So all right, anyways, let's go ahead and sum these vectors, right? So we have sum of the velocities in the x direction is equal to negative 9.19 meters per second plus 9.51. And if we do the math there, what do we get? I want to say, would that be 0.32? 0.32 positive? Yeah. Okay. I had it written down, but I'm like, I should be able to do that in my head. And this positive sign shows that this vector is actually going to point right. And if we look back up at our prediction, we had it pointed slightly left. And that's why this was a guess, right? I said that going in. I knew it was going to be slightly left, and slightly one direction or the other. And I guessed left because of how I drew my vectors, but it was actually slightly right, is what we're seeing here. Good. Okay. So I'm going to go ahead and that'll be our answer for sigma Vx. And we'll do the same thing with Vy. Now this one, we have two vectors that are pointed downward. So we're expecting a larger downward vector. All right, and we add those two together. I think we're going to get, let's see, that would be negative 12 point, what is that, 28? And this will be sum of the Vy. All right. Let me check something here. Oh, I see what I did wrong. I didn't even catch this, but I just did a second ago. So I need to be adding my Vy's, and look at that. I added 9.91 again by accident. So no one here to catch my mistake except myself there. So hopefully you saw that. Don't be like me and make a silly mistake like that. All right, so can we still add this or can I still add this in my head? Can you? I think you should be able to. Let's see what this is. Yeah, I don't think that's too bad. So I think we're thinking negative 10.8, right, 0.80 if you like, meters per second. All right, good. Whoops, okay. All right, so now what we're going to do is we're going to build our answer, which is our resultant, using these two vector sums, right? One of the vectors is going to be a larger negative vector. And so we're going to now sketch this new right triangle with our larger downward negative vector, right? Like this. And this is going to be added head to tail, right, with our other vector component. And these are components as well of our resultant. That's kind of what we're drawing here. So this vertical vector, I'm going to call it sigma Vy and label it as now I'm going to put the negative sign here, but I don't really need it because the vector is already pointing down. So the negative sign on the sigma Vy is redundant, right? Meaning that, yeah, the vector is already pointing down, so I don't really need the negative sign now. Okay. And the other vector that we're going to add head to tail with it is a smaller 0.32, and this is going to be sigma Vx. And notice I pointed it right. So I'm running a little low on room. Let me see if I can, I'm just going to go ahead and write right over the top of it and see if that is okay, if that works out. All right, so sigma Vx is going to equal 0.32 meters per second. All right, and then finally the answer that we're looking for is the addition problem of these two, which to add a Vy and a Vx, we need a right triangle. So, because what's going to happen is we added these vectors head to tail. I'm going to see if I can. Did we use a dotted line before for our result? And I think we did. So I'm going to try and do it again, even though I really struck. Whoa, eraser was on. Hold on 1 second. Little technical difficulties there. All right, so what I'm saying here is we're going to try and dotted line this. Really struggling to draw a dotted line. Just like that. Now, notice what I did there, right? And this is something that sometimes students forget, and that is, this is vector addition again, right? I have a start point. I have an end point. And I dotted the red line from the start to the end, right? This is vector addition, just like we practiced before. It has a right angle right here. And therefore it's a right triangle, right? Because it has a Vx and a Vy. And this is what's nicer about this. You might say, well, this is the same dang thing we just did up here. You just guessed the wrong direction. No, it's not the same. Here's why. Because with a right triangle, we can do Pythagorean theorem to find the value of r. But with this triangle, there's no right angle here, so we don't know what r is. But down here, we know that r, right, is the addition, the vector addition of 10.8 and 0.32. And we can't just simply add them because it's a right triangle. We have to use Pythagorean's theorem to add the two vectors. So I'm saying here that we have to use the fact that a squared plus b squared is equal to c squared. And once again, it doesn't matter what side you call A, so I'm going to go ahead and call this side A, I'm going to call this side B, and I'm going to call the resultant C. And that's what's important, right? Because the hypotenuse resultant being across from 90 has to be C because it gets its own side on this equation up here. And that's why it's so important. All right, so let's go ahead and plug those numbers in. So once again, I'm not really too worried about the negative sign on the 10.80 because the negative just means down, plus I'm squaring it, so it's going to go away anyways. I think we're going to see here that 0.32 squared isn't that much. All right, so we have something like this. 10.8 squared is going to equal 116.64 meters squared per second squared. The 0.32 squared is going to be very small. Like I said, it's going to equal 0.1024 meters squared per second squared. I apologize if this is getting rough to see. That meter looks, I can't even tell what that is, so I'm going to write that over. You know, it's bad if you write it and you can't tell what it is. So, all right, so we add those two together. Can we do that in our heads? I don't know. It's getting a little rough. It's late. Let's see, 116.7424. Yeah. Meters squared per second squared is equal to c squared. So we'll just square root both sides. And we're going to get the fact that c is equal to, and this is c is r, right? So I can make that change. I know I didn't, but I probably should, right? Because we're calling it r. Oh, this is awful. Let me see if I can write that again. All right, so we're going to say then that r is equal to the square root of that, which is 10.805. So just slightly larger than the other side, because it's just barely going to the right. And notice the meters and seconds got square rooted. Meters squared per second squared got square rooted as well, and became became meters per second. All right, so there we have it, 10.805. Now we're not done. We have to know what direction this points. And a lot of times students would just say down and right. And down and right is not good enough because a lot of vectors can point down and right. For instance, let's see, let me draw a coordinate axis. Okay, so let's have positive x here and positive y here, right? Okay, so what I'm trying to say is saying down and right isn't good enough because a lot of vectors can point down and right. For instance, that vector. For instance, that vector. Come on. For instance, that was going to get a straight line. For instance, that vector. For instance, that vector. And these are all different angles compared to the horizontal. So it's not good enough for us to just say down and right. All right, so what are we going to do? Well, we have one more formula to use here that's going to help us with this problem. So what we want to do is find the base of our resultant. The base of our resultant is right here at the star, right? This is where our base is because it points down and right. So this is the tail of the vector. So what I'm saying is we want to label our angle or have our angle coming from the side where the tail of the vector is. So I'm going to go ahead and draw the angle that we are going to find. It is right here. It is this small angle. Whoops. Let's go a little smaller there. Let's try this again. So let's go ahead and, it's this small angle right here. So I'm going to go ahead and label it theta. So what is that angle, right? And we have a right triangle. We have a known opposite, adjacent, and hypotenuse. So what we can do here to find this, right, is we said last time that we can use something called inverse tan, right? And what we did with that is we took our TOA formula, tan theta is equal to the op over the adjacent. We took our inverse tan function, which is like an undo button, and tan inverse will eat tan. So tan inverse cancels tan like that. And but if you do that to that side, then you got a tan inverse this side. So let's go ahead and rewrite that. So what I'm saying is you got theta left over, and theta is equal to tan inverse the op over the adjacent. So let's go ahead and plug in. We want to know theta. Let's plug in our opposite and our adjacent. Now, what is opposite theta? Is it Vx or Vy? It's obviously going to be Vx, right? Sum of the Vx. So we're saying that the opposite here is equal to that tiny vector, 0.32 meters per second. And it's very important you don't write a negative, or we don't have to worry about sign here. And let me show you what I mean, because on the adjacent, right, is going to be this Vy, and it has the negative 10.8. It will give us an incorrect mathematical answer to do the inverse tan of a negative sign. So like I said, I was ignoring the negative sign. Why? Because the vector is already pointing down, so I'm not worried about it a ton. Negative is just telling me down. So I'm going to go ahead and write just 10.80 without the negative sign. What about units? We'll check it out, right? Those units are going to cancel, and we are not going to worry about it. So we'll just divide 0.32 by 10.8, and then take the inverse tan of that. So if we do that, let's see, I think I'm going to need a calculator here, because I didn't do it this exact way last time. So let me go ahead and snag my calculator real quick. I think I have it here somewhere. Okay. All right, so make sure you can find your tan inverse button on your calculator too. So you have 0.32 divided by 10.8, which is equal to 0.0296. So I'm saying that this is going to equal, try and stick with black. I'm saying that this is going to equal the tan inverse of 0.0296. And let's see what that is. So we'll type that in, find that tan inverse key, try it at home. And I'm getting a very tiny angle, which is what we expected, of 1.697 degrees. So we'll say 1.70 degrees. Now, that still isn't good enough, because if we say down and right in 1.7 degrees, we don't talk about where, right? It's not 1.7 degrees from the horizontal, right? The horizontal isn't even drawn in here and is right here. There's the horizontal. So we can't say 1.7 degrees from the horizontal. So this is kind of tricky, right? What we should do here is reference it to the vertical, right? And the vertical just so happens to point down, right? Notice that. So we're going to say that the angle is 1.7 degrees, right? 1.70 degrees right from down. Notice it's not pointing straight down, right? It's 1.7 from down, but it's not left from down. It's not over here. It's right from down. So I have to be very careful in how I label this. So let me go ahead and write that down. So we're saying the answer is 1.70 degrees right from down. Now, some of you might be sitting there at home saying, well, couldn't we label it a different way? And if you're saying that, then that's very astute. That's correct. Let's look at another way we could have labeled it, right? And that is, what if we labeled it using, let's see, Let me get a different. What if we labeled this vector using this angle right here? Right? I don't like that. Let me try that again. What if we labeled it with this angle right here? What is this angle? It's this green angle right here. If that was the case and we labeled it with this green angle right here, then what angle is that? Well, it's the complement of 1.70 degrees, right? And so what would that be? I think that would be 88.3, right? Is that, yeah, 88.3, because 90 minus 2 is 88, but it's not quite 2, so we got that 0.3 left over. Okay, 88.3. So I'm saying that this angle also could have represented our R vector, except this one is referenced according to the horizontal. So we could have said 88.3 degrees down from right, because this horizontal points right. Notice that. Yeah. So we could have said 88.3 degrees down from right. All right, we're seeing how this is kind of difficult, right? So that was another way to label the same vector. Okay, so what is the final answer then? The final answer is this. The final answer is that R, the vector sum of these two vectors, is equal to 10.805, right? What I have written over here, let me see if I can get this. 10.805, it's this right here, right? Good little color here. It's this vector right here, 10.805 meters per second at 1.70 degrees right from down. So notice I put an at sign in there. I just say at, right? 1.70 degrees right from down. Or you could have said 10.805 meters per second at 88.3 degrees down from right. And they're both correct. So once again, way more accurate than what we did before, just by drawing head to tail and drawing our resultant start to end. Now we have a magnitude right here in orange, right? In this box right here, this is the magnitude or the amount of the vector. And we have a direction for the vector that is very specific. It is not just down and right. It is 1.70 right from down or 88.30 down from right. And the reason for that is all of these vectors are down and right. And that's just not good enough. So science is all about being exact. And you can see we are much more exact here this way. Okay, so next time I'll do another video going over another one on Thursday. Hopefully this will make more sense then if it didn't make sense today. And that's it. All right. Have a good day.